All right, let's look at another example of a related rates exercise. In my mind, this is like the classic Calculus 1 problem. If you go, it's called the ladder, the falling ladder problem. If you Google falling ladder calculus, there'll be so many websites, examples of this, slightly different takes on the question, but this is like the quintessential classic calculus related rates question. So let's see what it says. Consider a 13-foot long ladder leaning against a building. See figure below. I have a kind of a crude figure here for you. Suppose the base of the ladder is being pulled away from the building at a rate of 2 feet, feet per second. At the moment when the base of the ladder, here I'm going to change this. I think the answer will work out a little nicer to 5. I'll make sure to change that before you even see the notes. 5 feet away from the building. Determine the following 3 things. The rate of change of the top of the ladder as it slides down the wall of the building, the rate of change the area of the triangle formed, and the rate of change of the angle formed. Okay, so there's 3 of these very similar, or 3 different aspects basically of a triangle. So think about this. You have a building, you have a ladder, and that ladder is leaning up against the building, and the base is moving away, and the ladder's falling down. So you have this different shapes of triangle that are they're all right triangles, but it's going like this because the length of the ladder is not changing, but the base is being pulled out. So you start with almost like think of basically you're starting with almost like a 45 to 45 90 triangle, and eventually you get this really crazy scalene triangle until eventually the ladder hits the ground and there's no triangle. Okay. So that's kind of the setup here. It's kind of a ridiculous setup. Who's going to let a ladder scrape against the side of the building, messing up the side of the house or the building as it goes down. But anyway, it's just an interesting application. Okay, so what do we know? All right, well, we know that the ladder's 13 feet long. That's not changing. The length of the ladder is not changing as it falls down. So I guess we can go ahead and label this side of the triangle 13. It probably wouldn't be a bad idea to go ahead and label, because we are considering this triangle formed here. It's a right triangle. I mean, I'd probably call this H. Oh, I would call the B a base, or the base B, but that's going to look weird with D's and B's. Oh, let's just call that X, the base X. And it doesn't really matter how you label these, as long as you remember what your letters mean. So now that I have my triangle labeled, what can I get from the direction? So the hypotenuse of my triangle, the length of the ladder is 13. What other number am I given? I'm given 2. There's a rate of change of 2, a rate of 2 feet per second. Now, what does that refer to? Rate of 2 feet per second says the base of the ladder is being pulled away from the wall. So the rate of change of x, is 2 feet per second. Well, now we gotta be careful. Is it positive 2 or negative 2? Is the base x, is it getting bigger or smaller? So as x is being pulled away from the building, I think x is getting bigger. So we can say that dx dt, the rate of change of x, is positive 2. And we also want to consider the moment when the base of the ladder is 5 feet away from the building. So we want to consider the specific moment in time when x is 5. But remember, we can't go and plug things in until after we get our related rates equation. Now, speaking of a related rates equation, how might we relate the hypotenuse, 13, the base, and the height of a triangle? What formula might do that? Maybe the most notable formula ever that everybody knows about, maybe the Pythagorean theorem. That'll certainly relate the side h, the side x, and the hypotenuse 13. And so what we could say here, let's go over here. Part A, we can say that h squared plus x squared equals 13 squared. And by the way, with part A, we want to find the rate of change of the top of the ladder. So basically, we want to find the rate of change of the height of the ladder, because the top of the ladder is at the height is the top of the height of the triangle. So basically, we want to find the rate of change of the height. So we want to find dh dt. So we need dh dt. Okay. Now notice we know dx dt and we know x. So we are working with x's and h's. So the Pythagorean theorem is fine. Like, we don't have to eliminate any variables, because h's, x's, and 13 squared, that's fine. So we take the derivative of the left and right hand side with respect to time. So we get d dt of the entire left-hand side equals the derivative with respect to t of the entire right-hand side. Of course, that means that we take the derivatives on the left. There's two of them. We use the sum difference rule to take them individually. So d dt of h squared plus the derivative with respect to t of x squared. And we can go ahead and say that the right-hand side is what? The derivative is 0, because 13 squared is a constant. Okay, and now, notice we have, as always, we're taking the derivative with respect to t here at h term and an x term, so there's a variable mismatch. So we get 2h times dh dt plus 2x times dx dt equals 0. We're using the chain rule to multiply that or start to differentiate when we have that variable mismatch. Now, this is our related rates equation. Okay, we can go ahead and plug in what we know and solve for what we don't know. Well, what do we know? Well, actually, let's go ahead and solve for dh dt in the abstract, and then we'll plug in. So if we want to do that, what do we get? We get 2h dh dt. We'll subtract the negative 2x dx dt from both sides. And then to solve for dh dt, we divide both sides by 2h. So we get dh dt is negative 2x times dx dt, all divided by 2h. And now we can plug in, okay? We know what dx dt is 2. We know that x is 5. And so we get what? By the way, notice negative 2 and positive 2, we can get rid of those. So the numerator is going to be negative x, so that's negative 5, times dx dt is 2. Now the problem is, what's h? We're not told what h is, the height is, and basically we need to know the height at this moment in time. Now, what is this moment in time? The moment is when the base of the ladder is 5 feet away from the building. So we need to figure out the height at that time. Kind of like we did this in the example with the hot air balloon using trig. We had to find the height of the hot air balloon at that specific moment. Here, we need to find the height of the ladder when the base is 5 feet away from the wall. In other words, we're going to consider the specific triangle whenever the base is 5 feet away from the wall. And of course, the hypotenuse, the length of the ladder, is 13. That doesn't change. But we can use the Pythagorean theorem to find the specific value of h. H equals, well, of course, okay, I'll use the Pythagorean theorem, not simplified. We could say that h squared, not equals, that's the hypotenuse. H squared height here. H squared plus 5 squared equals 13 squared. In other words, h equals the square root of 13 squared minus 5 squared. Now 13 squared is what, 169, 5 squared is 25. So 169 minus 25 is 144. So the square root of 144 is 12. Okay, so h is 12. Now 12, that 12 only applies to the moment when the ladder's 5 feet away from the wall, but that's what we're concerned with. So we go in here, 12, and so what? That's negative 10 over 12. So what? Negative 5 over 6 is what that reduces to if you divide both the top and the bottom by 2. Now, what are the units? We're talking about the rate of change of the top of the ladder, so the rate of change of height, that's a length. So this would be what? We're talking about feet per second. Feet per second. So there's A. Cool. What about B? B is asking for the what? The rate of change of the area of the triangle formed by the ladder, the ground, and the building. Okay. All right, so we have our same basic triangle. What's the area of that triangle? Well, this is easy. What's the area of a triangle? 1/2 base times height. So what's our base? What's our height? 1/2 h is their height times x, the base. So there's our, that was the easy, way to relate the variables. We don't even need 13 right now. So what's the rate of change of the area of the triangle formed by that? So what are we looking for? We need the rate of change of the area, so we need the rate of change of the area, dA dt, A for area. So what do you get? If you differentiate both sides with respect to time, well, the left-hand side is exactly what we're after, dA dt. Now the right-hand side, notice that's h times x. Well, it's 1/2 times h times x. We can factor out the 1/2, but notice the remainder, h times x, is a product. That requires the product rule. So be careful here. 1/2 is going to be factored out, open some parentheses, and then we're going to use the product rule. So you do the derivative with respect to t of the first function h times the second function x plus the derivative with respect to t of the second function x times the first function h. That's going to give us dA dt equals 1/2. Okay, the derivative of h with respect to t, that's just dh dt times x plus the derivative of x with respect to t is dx dt with respect, times h is this. And now, okay, this is already solved for dA dt. That's what we want, the rate of change of the area. So it's just a matter of now plugging in all of the values that we either know or we'll have to find. So what's dH dt? Hey, that's what we've already found. dH dt, again, we're talking about the same moment in time when the ladder's 5 feet away from the base of the wall for all three of these questions. So dH dt, that's what we saw for in part A, -5/6. So -5/6 times x. X is when you're 5 feet away from the wall, so x is 5. Plus dx dt. Oh, sorry. Oh yeah, sorry. Dx dt is 2. That was given to us in the first paragraph. So 2. And now h we found in the last example was 12, right? Because that was the height of the triangle when the base of the triangle, the base of the ladder was 5 feet away from the wall. So h, again, we can reuse that information, 12 from the previous problem. So we get dA dt is, okay, I'm going to use a calculator to do this. What, that's -25/6 plus 2 times 12 is 24, divided by 2. And we get 119 over 12 if I type that into my calculator correctly. Let's see, let me double check. Negative 25 over 6, yeah, plus 24, yeah, divided by 2. Yeah, that's it. Now, what are the units? The units are going to be, we're talking about area, feet and area in minutes. Sorry, seconds. So it's going to be feet squared per second, because area is always measured in squared units. So feet squared per second. So here was our first answer. Here is our second answer for. So that sorry, I used a string of equalities here. So there we go. We found the rate of change, the height of the ladder in part A. In part B, we found the rate of change of the area of the triangle formed by the ground, the building, and the ladder. And what's part C? Part C is find the rate of change of the angle formed by the ladder and the building. Okay, the ladder and the building, let's put a theta there. That's the angle formed by the ladder and the building. Okay. Now we have a couple options here, and some of them are easier than others. We need a way to relate, I guess x's, because we know that dx dt is 2 and x is 5. Or, in fact, we know what h and dh dt is. We know that dh dt from part A is negative 5 over 6. And we know also that we're considering this moment when the ladder's 5 feet away from the building. So we can know that h is 12. So we have actually a couple different options here. We could actually, we're talking about an angle, so trig's probably advisable here. We could say use tangent. That would say tangent of theta is opposite over adjacent, x over h. But I think the smartest way to solve this would be to use the trig function that involves the hypotenuse. Because the hypotenuse is 13 is a constant. It's always easier to involve constants. Now, do we want to involve 13 in x or 13 in h? That'll dictate sine or cosine. Or we could use, of course, the reciprocal functions if you really want to. What could we say? We could say that sine. I'd probably use sine here. We could say for part C, we could say that sine of theta is what, opposite over hypotenuse? So x over 13. I think that's a good way. We can relate x and 13. We know, because we're going to eventually differentiate and get dx dt, okay, which we know is 2. And even though it's x over 13, the denominator is a constant, so we don't have to use the quotient rule. We can use the constant multiple rule to factor out a 1 over 13. So I think, yes, using sine here is a good idea. So here's the equation that relates theta and x. And now let's take the derivative of both sides with respect to t. So d dt of sine theta equals d dt, the derivative with respect to t, of what, x over 13. So what's the derivative of sine? Well, that's cosine theta. But since we took the derivative of theta with respect to t, we have to multiply by d theta dt equals. Now, okay, bear with me here. I'm going to do it. I usually don't like to combine 2 steps into one. Oh, I won't. I was tempted to, but I won't. I'm going to factor out the 1 over 13. Then multiply by the derivative with respect to t of x. So that gives me cosine theta times d theta dt equals 1 over 13 times the derivative of x with respect to t. Well, you get 1, and if you're applying the chain rule, the derivative of the outside function is x, the first power. You get 1, evaluate the inside function, which if you evaluate a constant function, you just get that constant function back. But then you multiply by dx dt, so dx dt. Okay, and that is our related rates equation. Okay, so now we can plug in the known values and solve for the unknown values. So we want the rate of change of the angle, so we need, I should have written this before, d theta dt. So I'm going to divide both sides by cosine theta to solve for d theta dt. So you have 1 over 13 times dx dt times 1 over cosine theta. Okay, so what do we get? What do we get here? D theta dt. Well, we have that 1 over 13, of course. What's dx dt? 2. Okay, oh, now we're to that same issue we've been at several times. What's cosine theta? Well, I don't know. Well, what we have to do is consider that triangle. Now, that triangle is the triangle that's formed when the hypotenuse is 13 and the base is 5 feet away from the wall. So, top left hand, that triangle that I already drew, that's the triangle we need to consider. So I can actually, we know that h is 12 now. So let's just go over here, give ourselves some room. And we can now label that as h, since we've shown that was h according to the Pythagorean. 12 is equal to h according to the Pythagorean theorem. And so now, okay, remember, theta is up here in the top corner. So what's cosine theta? Well, cosine theta is what? Adjacent over hypotenuse, is that right? Adjacent over hypotenuse. Oscar had a heap of apples. So cosine theta is 12 over 13. Now we're dividing by cosine of theta. So so we're dividing by a fraction. So 1 over that fraction, take the reciprocal. 13 over 2. Whoa, what do we get here? I wasn't expecting that. D theta dt. If we're dividing by cosine. Let me double check that because I didn't expect it to simplify so much. Cosine, the height was 12. That's 5, 13. Yeah, and cosine is adjacent over hypotenuse, so 12 over 13. We're dividing, so we have to find the reciprocal and multiply. It's 13. Oh, that's why. Okay, there was a typo. 13 over 12. I was about to say I was not expecting everything to simplify so much. So the 13s cancel out, but then we have 2 over 12, which gives us 1 over 6. So 2 over 12, and we need to give our units, of course. 1 over 6. Angle would be radians. So radians, and we're talking about seconds per second. So there's your quintessential ladder problem, related rates exercise that every calculus textbook out there uses, usually as an example. So I had to continue the tradition. Okay. So again, we had 3 different similar exercises, all about the same ladder falling down. We were in each instance considering the moment when the base of the ladder, so the base of the triangle, was 5 feet, and we were assuming that the base of the triangle was growing at a rate of 2 feet per second. Okay. Alrighty, I have plenty of examples. I've mentioned this 3 or 4 times now. I have lots of examples on my YouTube channel online. Plus, there's tons of examples on YouTube and elsewhere online if you want to see more examples of related rates. I know these can be confusing the first time you encounter them, but practice, consistent daily practice every day. That's how you get the hang of it. Okay. Let me know if you have any questions. I'll catch you in the next video.